All right, this video is on pH calculations of both strong acids and bases. And so we're going to start talking about acids first. So of course, what is not new to us is that we have a category of acids that are considered to be strong, which means they have 100% ionization. There are 7 strong acids. And even though we've seen this before, I think it's important for us to keep talking about them. HCl, HBr, HI, HNO3, H2SO4, HClO4, and HClO3. Okay, now since strong acids ionize 100% of the time, we can make a big connection between the concentration of the acid and the concentration of the H+. And so this is what I mean. So if I have HCl, for example, which we know, of course, is a strong acid, then the ionization occurs 100% of the time. So if, and I'm just making this number up, right? So if my acid is 0.25 molar, then all of that ionizes, and so my concentration of H+ is 0.25 molar, and my concentration of HCl is 0.25 molar. So since we have 100% ionization, we can do a direct relationship between how much H+ is in the solution and the concentration of the acid to begin with, or the original concentration. And that's a really big deal. We're going to see later when we have an acid that's not strong that I cannot make that connection. Okay, so from here we can proceed with calculating pHs for strong acids, and it's a very simple idea to do. So look at these practice. The first one says, what is the pH of a 0.04 molar solution of HClO4? Well, of course, this is strong. And so if I had a solution of this, ionization occurs 100% of the time. And so my 0.04 molar acid gives me 0.04 molar H+, which of course now I can use to do my pH calculation by taking the negative log of 0.040. I could use my approximation technique here if I wanted to. It would be helpful for me to turn that into scientific notation, right? -2. So I'm going to approximate that pH is, remember we subtract 1 from the exponent, so it's going to be approximately 1 point something. And if I punch it on the calculator, it comes out to be, let's see, remember two sig figs means 2 decimal places, so it comes out to be 1.40 is my pH. Okay, and that matches with my approximation. And that is how simple it is to calculate the pH of a strong acid. Okay, we can of course go the other direction, because if we know pH, then we also know H+ concentration. So it says an aqueous solution of HNO3 has a pH of 2.34. What's the concentration of the acid? So I know I can find the H+ concentration by taking 10, raising it to the negative pH. So 10 to the negative 2.34 is going to give me a concentration of let's see, 2 decimal places, so 2 sig figs, right? So molar. That's my H+ concentration. But because nitric acid has 100% ionization, then I can say that if this concentration is 0.0046, so was my original concentration of the acid. So not only is 0.0046 molar the concentration of the H+, but it's also the concentration of the acid that I started with. So strong acid calculations are very simple for us because we can make this direct correlation between the concentration of the H+ and the concentration of the acid, since it's 100% ionization. The same thing can be said for bases. We can do the same idea because, of course, strong bases have 100% ionization. Remember that your strong bases are your group 1 hydroxides and your heavy group 2 hydroxides. And that was calcium hydroxide, strontium, and barium. So again, because they have a 100% ionization, for example, something with barium hydroxide, okay, if I started with a 2 molar solution, well, I would get a 0.2 molar concentration of the barium ion, but I would get double, right, the concentration of the hydroxide ion. But I can always know this number because it's 100% ionization, and I can use that number to then calculate a pOH, a pH, and so on and so forth. So same idea applies. So 2 practice problems. So what's the pH of these 2 situations? So in A, they give me the NaOH concentration is equal to 0.028. Well, we know that that's also going to be the OH minus concentration because, of course, this is 100% and it's a 1-to-1 ratio, right? 1-to-1. So if that is the OH minus concentration, I can take the negative log of that to find the pOH. So negative log let's see, 2 sig fig, so 2 decimal places. So 1.55 is my pOH, but remember they're asking me for pH. So 14 minus 1.55 gives me 12.45. And that pH shouldn't surprise you because sodium hydroxide, of course, is a base, and this is a pretty basic pH. And then in B, same idea, but this time I'm given calcium hydroxide. So we should see quite quickly that it's a 2-to-1 relationship. So when the concentration of calcium hydroxide is equal to 0.0011, the OH concentration is equal to 0.0022, and I can do the same thing. pOH is going to be the negative log. So 2.66. Again, I'm looking for pH, so subtract that from 14. Again, a very basic pH. So if we had to put a takeaway statement here, it's that strong acids and bases have, we can easily calculate pH due to the 100% ionization. Okay, and for that matter, we can back up a pH. We can back up an H plus concentration or an OH minus concentration to be the initial concentration of the acid or the base from the ratio and the 100% ionization. So I hope what you're seeing is that the strong calculations are going to be your easy calculations, but when we get to do weak acids and bases, that's a whole different ballgame because the ionization is no longer 100%, and this relationship becomes much more difficult.